Welcome. This is Professor Nathan Weezy of Marquette University. This section we're going to talk about the three-phase PLL, part 2. And what we're going to do here is talk about implementing this in the digital fashion now using a floating point variant, and we're going to use the backwards Euler approximation. Okay, so let's just quickly recall. We have a controller. This is what we're trying to design. What we did in the previous section was a continuous time one, and it was a PI controller. We're going to do a PI controller again here, but we're just going to convert it to the Z domain. This is our ABC to DQ transform, and just recall that really this is the thing that generates the error because we want to drive Q to 0. So think of that as almost our detector, if you will. This is the center frequency. That's essentially what we want to lock around. This is our integrator, our 1 over S in the real time, which we've approximated here. And of course, this is our mod. This is just doing the phase wrapping. So this has no gain to it in terms of phase because all it's doing is wrapping. And this is just so we don't have overflow in the number system that we represented in. For example, if we use floating point here, this could grow so large that it would roll over or overflow or underflow or anything like that. Okay, so let's talk about the design. Design is going to be very similar, except for we're going to transform this into the Z domain. Go ahead and do that. First thing I'm going to do is I'm going to show some MATLAB script code that I've done to design this controller. So we set VG to 170. Again, this is the gain of the grid voltage. Zeta, that's our damping ratio. And again, we could pick a different one. That's why it's nice to have it scriptable. And this is a natural frequency. We can pick different values here, whatever we'd like. And equation 6 and 7, this is the gains for the controller, Ki and Kp. All right, so once we have those calculated, essentially the controller is designed, but now we want to go ahead and convert this controller over to the Z domain. So first things first, we create a transfer function of S. So S is now a transfer function object within the MATLAB workspace, and we can use that to instantly draw equations for transfer functions. An interesting thing here is we're going to use this option structure, which you can use for passing to Bode function. And all we're going to do is the default is in radians, and I generally like to look at it in hertz. So we're just going to set hertz in terms of the Bode plot stuff. Line 12, this is our controller. So we're just defining our controller as a function of our gains, Ki and Kp. 13, that's the gain of the rest of the gain of the stage. Vg is the constant gain of the detector, and 1 over S is the integrator gain. And that's all we have. And then essentially this is our open loop gain. So we multiply those two together. And then we calculate closed loop response. And this min real, let's talk about this quick. This is a nice function. If you have a pole and a 0, MATLAB, and they're the same, like you have S over 1 plus S over 1, MATLAB will not automatically pole cancel. And if you call min real on a transfer function that's got a matching 0 and pole, it'll then give you basically the minimum realization of the transfer function. So sometimes you have to do that because you have some poles and zeros that don't cancel and you'd like to get rid of them. Okay, cool. So 17 here, this 17, 18, and 19 will give us a Bode plot. Essentially, we can look at the gain and phase of our controller, of our open loop response and closed loop response to make sure that we met our bandwidth spec and our damping ratio spec, etc. All right, so how do we convert this to an actual controller in the digital domain? That's not too hard. First, this line here is the sampling time. So right here I have it set for 10 kilohertz, and that's going to be plenty enough for this application, especially when you're trying to lock to like 60 hertz. I mean, one order of magnitude is 600 hertz, another order is 6 kilohertz, or at least 2 orders of magnitude higher than what we're trying to lock to, which is in general pretty good. This is our Z transform. So we create a transfer function object in the Z domain, capital Z, with a sampling time of 10 microseconds. And then we can write 25, which is essentially the backwards Euler approximation for S approx, right? And then what we do is we go ahead and feed that into 26. So this will be our digital controller using the backwards approximation. And of course, I went ahead and in line 27 and 28 calculated them using different approximations like zero order whole and Tustin using MATLAB's predefined function C to D, which will convert a continuous time system to discrete using different approximations. The only downside is they don't have one for backwards Euler, so I just made it up by myself there. Okay, cool. So what'll happen now is we'll actually have the transfer functions for those in the Z domain, but what I'd like to really get is the coefficients of the filter so that I can put them directly into my C code on my microcontroller. So these nice little lines of code here, 31 through 36, what's going on here is first, we're grabbing the numerator coefficients of the digital controller, and they're actually in a cell. That's why this curly brace 1. And in this cell is a vector of the coefficients. So this will be a vector of coefficients, and the last thing I'm doing is calling single around it, and what that is doing is converting those from double floating point, because that's the default number system in MATLAB, to a single precision floating point, which is probably in general what you will have if you have a floating point unit. That's the type you generally have on low-cost microcontrollers is a single precision floating point. So this B coefficient and A coefficient, line 31 and 32, will be vectors of single precision floating point numbers, okay? And then what we'll do is just print them out in a nice, easy fashion in the prompt. That's line 33 through 36, defined in C code. So I just wrote float A1 equals %F, where %F is the first element in A coefficient vector, which is a single precision floating point number. Okay, so what actually comes out of this? This is split across 2 pages, I apologize. But like for instance, float A1 is just 1, float A0 is -1, okay, that's not too bad. Float B1 is 5.406614, and float B0 is -5.1743888. And again, these are in single precision. And literally what I do is I can just take this code that spits out from MATLAB, this stuff right here, and literally paste it into my controller code and compile it for my microcontroller, and I'm off. I have my controller designed. Okay, so this was a continuous time controller that we designed in the previous section we talked about. This is the controller in the Z domain now, our digital controller. And you can see the coefficients match up with the floats up here. So we have good matching agreement. So you can see one thing here is just the way I wrote the code here. It's not displaying all the digits out, but this is the more accurate representation in single precision floating point. And this is also the more accurate representation in single precision floating point. So let me go ahead and just point to where these all go. So that one's here. That one, of course, is here. And then, of course, you see the 1 minus 1, which is down here. Okay, so you can see those are the gains of our controller. So there's a pole at 1 and a 0 at 0.957. So we're stable when we look at the controller in terms of internal mode stability. Let's go ahead and look at the output of our controllers to a couple of different transients that you may see on the line. This is similar to what we did in continuous time, but now we actually have a backwards Euler discrete digital controller. So what happens here is we're going to have a voltage step of 17 volts at 0.011 in time. So what happens here is if you look at the voltage, you see this step right here of about 17 volts in red. And it actually happens in yellow and blue. Pretty hard to see, but it is indeed there. Okay, so what's the effect? From the digital sense, our d-axis looks exactly the same, except for at this time, we jump about 17 volts on the d-axis. Q doesn't change. We remain locked, which is really nice. We just had a magnitude change. We didn't have a phase or a frequency. So that's good. We remain locked here. Control output looks the same. And if you look at our phase, you can see it's digitized here, which is great. This is what you would expect to see in a digital controller. Okay, so the response here isn't any different than what we saw in the continuous time variant, except for our values are now digital. They're discrete time steps. You have some precision, finite precision. Let's look now what happens when we have a step in line voltages. Sorry, excuse me, a phase step of 0.62 radians. This is a pretty extreme case, but let's just go ahead and illustrate what happens here. So we're going to have this happen at about 0.21 in time. So I'm just draw this line straight down. You can see, actually, let me do this a different way. You can see that we have something interesting here. We have a step in phase, so if you look at the voltages, you can see how we have this discrete step. It happens instantaneously. This one steps here, this one steps there, and blue steps like that. This is a pretty drastic case for voltages, but that's the transient. And what happens is, because we lose our Q-axis alignment right away, immediately Q jumps up like this. It's saying, oh, we are not aligned. And so what happens is that this, essentially Q is our error. So if this is non-zero, you're going to get something out of your controller. So the controller actuator output jumps from 0 up to like 600. Like, hey, we're misaligned. Let's push the system towards alignment here. And you can see as we push harder and harder and time goes on here, you can see even in the phase response, we're like, oh, we need to speed up because there's a jump. You see this kind of curvature, and then you can see about here we're locked in again. So somewhere about, let's call it 5 milliseconds later, about here is where we're locked in. And we can tell because Q is driven back to essentially 0 again. And we have no error in that after that phase jump. So you can see this controller is working nice. Just like the continuous time variant, even in the digital domain here, you can see our phase is digitized. Of course, it's a digital controller. Our voltages that come into our controller are digitized because we're sampling at a fixed frequency. Even our control actuation is digitized. Everything is digitized, and it's all digitized at 10 kilohertz here. All right, let's look at another transient here. We have a transient at 0.31 seconds, and this is a pretty drastic one. We're going to have a frequency step. Now this is another very challenging transient that you wouldn't normally see this drastic of a step in hertz discretely like this. But what's happening is we go from 60 hertz instantaneously to 61 hertz. It's hard to see when you look at these voltages. Are they 60 or 61? But we jump right at 0.31. And you can see that's happening because if you look at the Q-axis, the Q-axis detects it right away. It comes up and then it comes down and settles. Okay? And what happens now, because of the actuation, we have to actuate in a positive fashion in order to speed the system up and to catch up to 61 hertz. And the other thing that I'll say here is the control output does not settle to 0 again, because it's going to settle to whatever the control output is plus the center frequency. Well, we're at 61 hertz and the center is 60, so the control output is going to settle at about 1 hertz in order for us to lock onto 61 hertz, which is what it's doing here. But this is in radians, okay? So it's not in hertz, that's why it's not 1. Okay. Let's see, that would be about 6.28 radians, which, this axis is 10, so it's looking about right. All right, let's move on to another transient we have here. This will be our last transient. This is a very challenging one. Essentially, we're going to have an unbalance of phase voltages at 0.35 in time. Now, this could definitely happen. This is a real-world type scenario, especially if you're dealing with three-phase. And let's zoom in here quick. You can see I'm only doing it to the red phase. It's a 10% unbalance. And it's a big jump. And what happens when you have an unbalance now is that you have positive, negative, and zero sequence voltages. All right? And so what that really translates to is you're going to have a harmonic, second harmonic, which you can see in Q and you can also see in D. So the interesting thing here is that you're not going to be able to drive Q to 0 here because your voltages are unbalanced. Okay, so what you're going to want to do is drive the average of Q, the average over that harmonic, to 0. And if you do that, then again you can be locked here. So the average right down the middle. If you can drive that to 0, then you can remain locked, even though you have this oscillation. Now you can see that because Q is oscillating, the controller is just oscillating back and forth in terms of actuation output, in trying to track this. The good thing though is that we remain locked in this case, even though we have this harmonic. But you can see this visually. So at 0 phase, we're at the peak of phase A, which is essentially we're locked to cosine. So assume cosine of the blue waveform was 0. So cosine of 0 would be the max amplitude. So you can see visually here we are indeed locked to this, even in the presence of this harmonic component or unbalance. There really wasn't much of a transient to the system. Now, what you could do in a more advanced case for this PLL is to break your three-phase voltages up into positive sequence, negative sequence, and zero sequence. And then essentially what you want to do is lock to the positive sequence voltages. And that way it'll remove all issues related to unbalance. You won't even see this oscillation in the unbalance because your positive sequence will always be balanced when you break it up into positive, negative, and zero. And what will happen is when you have an unbalance on the voltages, it'll show up in like your zero sequence components. Okay, cool. This concludes the discussion on the three-phase PLL using floating point numbers and using the backwards Euler approximation.